Today we are talking about energy transmission and conversion. As you can see on the screen, our content is for today: the production of electricity, generators, transformers, the path of electricity, energy transmission and conversion, energy transport, energy conversion, energy storage, energy carriers, sustainable energy, carbon dioxide emissions. Let's start the production of electricity. Start from the generators, the driving springs of the process. Generators are devices or equipment that can produce electrical energy. These devices can operate on different principles and use different energy carriers. Some common types of generators are electric generators. These devices convert mechanical energy into electrical energy. Most often they are based on the principle of Faraday induction, where a rotating coil induces a magnetic field by means of a magnet and the resulting electric current is collected. 2. Wind generators. These generators use wind energy to produce electricity. The rotating blades rotate in response to the wind and convert the rotational motion from their movement into electricity. 3. Hydroelectric generators. Hydroelectric generators harness the kinetic energy of rivers, streams, or waterfalls. They usually use water wheels or turbines that drive the generator to produce electricity. 4. Solar generators. These generators use solar energy to convert it into electricity. They use solar panels or solar cells that convert the sun's rays directly into electricity. 5. Diesel generators. These generators use diesel engines to convert kinetic energy into electrical energy. They are typically used in situations where there is no regular source of electricity or where a portable power source is needed. These are just a few examples of the types of generators. Generators are widely used devices and can be found in a wide range of applications, such as energy, domestic, industrial, and transport. Electricity can be generated in many different ways, but most of the methods basically involve setting small or large generators in motion. The energy needed to power them can come from renewable and non-renewable resources. The most controversial point is that renewable resources are typically only available in a continuous supply, or a special type of hydroelectric power plant uses sea waves, while fossil fuels are severely damaging to the environment in exchange for stability. Generating electricity is a simple physical process. You could say that a generator is essentially an electric motor running in reverse, and as such does not actually produce power. Instead, mechanical or chemical energy is converted into electrical energy. The mechanical energy added is used to force the movement of electrical charges in the coil wire through an external electrical circuit. Electric generators work on the principle of electromagnetic induction. Scientist Michael Faraday discovered this phenomenon in 1831 when, moving a magnet through a loop of wire, he noticed that an electric current was triggered in the wire. What is the difference between a generator and a solar panel? We have mentioned that the two most common methods of energy production are the use of generators or solar panels, more specifically photovoltaic (PV) panels. While generators are basically reverse electric motors and convert kinetic energy into electricity, solar panels work in a completely different way. Photovoltaic, or photoelectricity, refers to the direct conversion of sunlight into electricity at the atomic level. A photovoltaic cell produces electricity by the action of incoming photons. The photovoltaic effect was discovered in 1839 by the French physicist Edmond Becquerel. How is electricity transported and distributed? Once the electricity is on, it's worth getting to work. but it would be a hassle to plug your mobile into a hydroelectric power station or solar park every time it runs out. Mainly because the electricity generated is still far from suitable for residential use. It has to be converted, i.e., transformed, first. It is important to clarify and highlight the definition of transformers. How a transformer works? A transformer can step the voltage up or down based on the principle of magnetic induction. A transformer consists of two or more coils of insulated wire wound around an iron core. When voltage is applied to one coil, primary or input coil, it magnetizes the iron core, which induces voltage in the other coil, secondary or output coil. The path of electricity from the transformer to the household is usually as follows. 1. Transformer stations. High voltage electricity is brought to transformer stations by transmission lines. Transformers and transformer stations convert high voltage, usually 110 kV or 220 kV, alternating current to lower voltage, usually 10 kV or 20 kV, to make it easier to transmit. 2. Poles and wires. Lower voltage current is transmitted through poles or wires within a city or town. This current is routed from the transformer station to the households. 3. Main distribution boxes. Houses or apartments usually have main distribution boxes in which main distribution switches, fuses, or circuit breakers are located. These devices provide protection and control of local circuits. 4. Distribution wiring. Wires carry power from the distribution boxes to individual consumer points, such as outlets and lighting points in the house. 5. Consumer points. Consumer points, such as outlets, lighting, or appliances, receive the electricity in the household or building. The devices connected here use the electricity for their intended purpose, such as lighting, heating, cooling, running appliances, etc. It is important to note that the path of the electricity can be more complex and may consist of several stages, depending on the type of supply and distribution system in a given area. The above description provides a general overview of the path of electricity from transformer to household, but in reality it may vary based on the details and the specific municipal system. Why is it important that all the steps are coordinated and seamless? There are three main reasons why it is important to optimize the whole process. 1. The better the efficiency of transmission and transformation, the more electrical devices the same network can serve. 2. The less we waste, the better we protect the environment. 3. A poorly functioning system results in additional costs, which are ultimately paid for by the consumers, i.e., us. Really significant facts are that 1. Only use what you use and for as long as you use it. It is hardly necessary to explain further why we can save money in this way. To explain why we need to use only what is under power is consuming electricity. It may be minimal at one time, but many little ones go a long way. Why spend thousands of extra forints a year? 2. Modernize your appliances. This is a more expensive solution, but in the medium term it is worth replacing old, energy-intensive appliances with energy-saving ones. Of course, avoid unnecessary overspending by calculating whether it's worth replacing your old B, D, or even F-rated fridge or washing machine with an A or A+ rated one. 3. Invest in renewable energy production. If you can, consider investing in solar panels or geothermal heating systems. It's true that both take years to pay for themselves, but typically a photovoltaic system will start to pay for itself after a good 10 years. Plus 1. Upgrading the power generation and transmission network. Although not a residential scale optimization, it is a welcome addition. By replacing decades-old, outdated systems with modern, much more efficient infrastructure, operators can cut their losses significantly. And we need to develop and evolve because we have a planet. Just as infrastructure is becoming greener, there is plenty of work to be done on electricity services. Energy transmission and transformation is the process of transferring and transforming energy from production sites to consumers. Energy is often produced at remote locations, such as power plants or renewable energy sources, and the consumption sites may be further away, such as households or industrial installations. Not consume natural resources and are produced in an environmentally friendly way. The concept of energy transport. Energy transport refers to the transmission of energy produced or generated to consumers or other locations. This allows energy to be transported to areas where it is needed, such as homes, businesses, industrial facilities. Energy transport means the transfer of energy to places of use. Different modes of transport and infrastructures can be used to transfer energy, such as pipelines, tubes, ships, trains, or special containers. Electricity is usually transported by wires or grids, while gas or oil moves through pipes or tanks. The concept of energy conversion. The energy produced is usually available in a particular form, e.g., electricity, heat or mechanical energy, and may not be of the right nature for the places where it is consumed. In energy conversion systems, different types of energy are converted into a form that is easier to transport and use. For example, generators convert mechanical energy into electricity, while heat exchangers convert thermal energy into other forms of heat. In the process of energy conversion, energy is transformed from one form into another. For example, electrical energy is converted into thermal energy in a heat exchanger. Let's continue with the types of energy conversion. Energy conversion is the transformation of energy from one form to another. The purpose of converting energy between different forms is usually to make it more usable or easier to use. The following are some examples of energy conversion. 1. Electrical energy conversion. Electrical energy conversion is the conversion of electricity into another form. For example, mechanical energy, such as wind or water energy, is converted into electrical energy by generators. Inverters convert direct current into alternating current or vice versa. 2. Thermal energy conversion. For example, heat pumps can be used to extract heat energy from the environment and convert it into heat energy that can be used for cooling or heating. Heat energy can also be converted into other forms by water heaters, boilers, or solar panels. 3. Chemical energy conversion. For example, when fuels are burned, chemical energy is converted into thermal energy. Electrochemical cells, such as batteries, convert chemical energy into electrical energy. 4. Mechanical energy conversion. For example, wind turbines convert wind energy into mechanical torque. Generators convert mechanical motion into electrical energy. Energy conversion is a widely used process in energy engineering and helps to harness and use available energy resources in different ways. This makes energy use more efficient and versatile in different industries and in our daily lives. Efficiency, reliability, and sustainability are important considerations in energy transport and conversion. Environmental impacts and economic efficiency must be taken into account when choosing energy carriers and designing infrastructure. The development of advanced technologies and energy-efficient systems will help to make energy transport and transformation more efficient and sustainable. Energy storage provides a way to shift energy in time between production and consumption cycles or due to distance. Storage systems, such as batteries, hydrogen storage or reservoirs, can store energy and use it later. Energy storage refers to the use of different methods to store energy in some form for later use or recycling if necessary. Energy storage plays an important role in the field of energetics, as it allows to increase the efficiency of energy systems, to balance energy production and consumption, to provide flexible energy supply, and to ensure the availability of reserve energy. Energy storage can take different forms depending on the energy source or energy conversion system used. Some examples of energy storage technologies are: 1. Chemical energy storage. Batteries. Chemical reactions are used to store electrical energy, e.g., lithium-ion batteries. Hydrogen and oxygen are produced from water using electric current and then recycled for later use in fuel cells. 2. Mechanical energy storage. Compressed air energy storage systems. Electrical energy is used to convert electricity into compressed air, which can be converted back into mechanical work for later use. Air drums. Air drums are used to store and return mechanical energy by varying the pressure of compressed air. 3. Thermal energy storage. Heat storage materials. Special materials are used to store and subsequently use thermal energy, such as heat accumulators or heat storage in solar energy systems. 4. Electromagnetic energy storage. Superconducting coils. Coils made of superconducting materials can be used to store and return electromagnetic energy. These are just a few examples of energy storage technologies, and the industry is constantly evolving with new and more efficient solutions. Energy storage is key to integrating renewable energy sources, improving the efficiency of transmission lines, stabilizing energy supplies, and increasing the resilience of grids. Types of batteries. Lead-acid batteries. Lead-acid batteries are the most common on the market, are simple and easy to use. They are simple and easy to use. Their life, durability, and lifetime are very short, but they have a longer lifetime and are less expensive than modern batteries. When used up, they are considered hazardous waste, as the acid content can significantly damage groundwater and lead is highly toxic. Most lead-acid batteries can be recycled if the right rules are followed. Lithium-ion batteries. They have quickly become popular because they do not require much maintenance, have a long lifespan, and have a good charging capacity. They have been most rapidly adopted as batteries for smartphones and laptops because of their lightweight and rechargeability. Today, lithium-ion batteries can be found in the design of solar systems. Redox flow batteries. Flow batteries store the electrical charge using water-based zinc and bromine solutions and vanadium. They have high efficiency and fast recharge rates, but are expensive. Sodium nickel chloride batteries. Sodium nickel chloride batteries are safe and reliable. In extreme. However, they have a short lifetime, low discharge depth, and are extremely expensive. When choosing a battery, you should consider the following aspects. Energy storage capacity. The energy storage capacity of the battery, its rated output, is a key factor in the selection. Type. Nowadays, it makes sense to choose high-quality lithium-ion batteries, which, together with your solar system, can serve your needs for a long time and provide security in case of power outages. Lifetime. Battery life depends on several factors. Discharge depth. The extent to which the battery is discharged during operation depends on the discharge depth. A higher value means a longer battery life. Temperature. Batteries can heat up during operation. For better battery life, keep batteries at cooler temperatures. Number of cycles means the number of times the battery can be fully charged and discharged. Each time a battery is fully discharged and recharged represents one charge cycle. By definition, a lower number of cycles implies a shorter lifetime. Cost. Although at first glance, the cost of the battery increases the "not low anyway" expenditure associated with a solar PV system. But it makes sense to choose a quality, long-life system. What considerations should be taken into account when siting the storage battery? 1. Ventilation and heat sources. Batteries should not be placed in too confined a space. The room should be well ventilated, kept away from heat sources, including direct sunlight. 2. Accessibility. Batteries should be easily accessible for servicing and maintenance. 3. Protection. Batteries must be protected from the weather and rodents. They should be kept out of the reach of children. 4. Disconnection. Ensure that batteries can be quickly disconnected. This should be taken into account by installers during installation. 5. Weight. The physical size of the batteries, and therefore their weight, up to more than 100 kilograms, will depend on the size of the system and the required lead time. If necessary, the planned room should be checked from a structural point of view. 6. Outdoor or indoor. Enclosed installation is recommended, but accessibility and ventilation are paramount. Avoid areas exposed to direct sunlight or strong heat gain. Reality. A saltwater battery is a type of power source in which chemical energy is stored by means of saltwater electrolyte. This type of battery usually consists of two electrical cells separated by a saltwater electrolyte. The operation of a saltwater battery is as follows. 1. Electrochemical reactions. Electrochemical reactions take place at the positive electrode, anode, and the negative electrode, cathode, of the battery. 2. Electrodes. The anode and cathode electrodes are made of materials that are capable of carrying out chemical reactions in the electrolyte. For example, anode electrodes are usually made up of lead dioxide, PbO2, while cathode electrodes may contain lead, Pb, or other substances. 3. This allows the flow of electrical charge carriers, i.e., ions, in the electrolyte when the battery is charged or discharged. 4. Electric current. During electrochemical reactions, electrons flow between the anode and cathode through the external circuit. This process generates electricity that can be used to power appliances or equipment. The advantages of saltwater batteries include relatively low cost, high reliability, and long life. However, these batteries are large in size and have a higher mass, so they generally have a lower energy density compared to other types of batteries. Saltwater batteries are used, for example, in marine applications, solar energy storage, uninterruptible power supplies, and industrial applications where high capacity and reliability are important considerations. Energy carriers are substances or forms that carry energy and enable the transfer and storage of energy. Energy carriers can take different physical or chemical forms, and different types of energy carriers are needed for different energy production and use processes. Some common types of energy carriers are listed below. 1. Fossil fuels. Examples: coal, oil, petroleum, natural gas. Fossil fuels are the remains of plant and animal matter that have decomposed over time. They are widely used as energy sources, especially in power plants, transport, and heating. 2. Renewable energy sources. Examples: solar, wind, hydro, biomass, geothermal. Renewable energy sources come from natural resources that are constantly renewed. Renewable energy sources are an environmentally friendly alternative to fossil fuels. 3. Nuclear energy. Nuclear energy is generated in nuclear reactors, where the decay of radioactive materials generates thermal energy. The resulting thermal energy produces steam that drives turbine generator systems to produce electricity. 4. Electricity. Electrical energy is the most commonly used form of energy transfer. Electricity generation is the most common form of electricity. 5. Hydrogen. Hydrogen is an energy carrier in a gaseous state that allows for long-term storage and transport. Hydrogen can be used as an energy carrier in fuel cells or combustion engines for conversion to electricity or mechanical work. The choice of the appropriate energy carrier depends on the specific application and energy demand, taking into account economic, environmental, and sustainability aspects. Sustainable energy means energy sources that are sustainable in the long term, do not deplete natural resources, and are produced in an environmentally friendly way. Last but not least, talk about carbon dioxide emissions. Carbon dioxide emissions are a measure of the emission of carbon dioxide, CO2, gas, which is often present in combustion products. Carbon dioxide emissions contribute to the increase in greenhouse gas concentrations and the problem of climate change. Today's lesson is based on the references and resources listed here. As we come to the end of our lesson, I would like to thank you for your attention and wish you a good learning experience.